Somewhere beyond the stars you see at night, past the glowing fog of ancient galaxies and the dying light of forgotten suns, lies a question so massive, so impossible, it breaks the rules of space, time, and even logic. Does the universe have an edge? Not just a border we haven't yet reached, but a real, physical, limita final frontier beyond which there is nothing. Not dark matter, not silence, nothing. And if that edge doesn't exist, then what does that mean for everything we think we know? For everything we are? We are raised in boundaries. Our maps end at coasts, our cities at borders, our lives inside bodies with beating hearts and closed systems. Even infinity feels like a number too big to grasp something abstract, decorative, poetic. But when we talk about the edge of the universe, we're not dealing in poetry. We're dealing in physics, in measurements, in the sharpest theories, and the most advanced telescopes human minds have ever created. And still, no matter how far we look, the edge never shows itself. The further we reach, the more the universe unfolds, like a hallway in a dream that grows longer as you walk. And yet, something doesn't add up. Because while we keep discovering more stars, more galaxies, more lightsome of the math, the deepest laws of physics suggest there should be a limit. There must be a limit. Otherwise, the consequences are staggering. If there's no edge, then the universe might be infinite. And if it's infinite, then every possible configuration of matter, energy, and life not only exists somewhere, it exists infinite times. There are versions of you out there, right now, not just similar, but identical. Reading these same words, sitting in the same room, blinking at the same time, thinking the same thought, and also others that are slightly different. You with a scar you don't remember getting. You who took a different path. You who never existed at all. That's not science fiction. That's the cold, logical fallout of an infinite universe. And it's the kind of mystery that cosmologists wrestle with every day. But it's not just about infinity. It's about contradiction. Because some of our best theories about the universe's general relativity, quantum mechanics, cosmic inflation, they don't agree. They argue. They clash. And when you ask them to describe the edge of the universe, they either go silent or explode into paradoxes. One says the universe is flat. Another says it's curved. One suggests it had a beginning, a big bang. Another suggests that before the bang, there was something LC cycle, a bounce, a landscape of countless births and deaths. Some theories suggest that the edge is an illusion, that there's nothing to find, and even the idea of a boundary is born from our limited perception. Others insist that beyond what we can see lies a vast multiverse, where the laws of physics themselves shift like dialects across countries we will never visit. And through all of this, one fact remains: we are limited, not by imagination, but by light. The speed of light defines the size of our observable universe, about 93 billion light-years across. That's not the size of the universe. That's just what we can see. Because light takes time to travel, and the universe is only 13.8 billion years old. Everything we know about the cosmos is bound inside that luminous shell. We call it the observable universe. But what lies beyond? More galaxies? A void? The edge? Or something stranger? The truth is, we don't know. And that's what makes this story so powerful. It's a story still being written by scientists, by instruments, by thinkers who stare into equations and ask whether space and time themselves are real or just emergent illusions. It's a story filled with wonder and fear, with beauty and dread, with mind-expanding questions that challenge what it means to exist at all. It's about whether the universe is a bubble inside a grander reality, or whether reality has no outside den beyond. Just is. And it matters, because our place in the universe isn't just about location. It's about meaning. If we are finite in an infinite cosmos, then every choice, every life, every star that ever burned becomes part of a larger whole-lone pattern among infinite patterns. But if the universe does have an edge, then there's something out there, something more, maybe another kind of space, maybe an end, or maybe something we don't have the words for yet. Either way, the question cuts deep, because this isn't just about astronomy, it's about identity, about how we see ourselves, about how we explain our lives to ourselves. And the closer we get to the edge of the universe, the closer we come to the edge of understanding and maybe even the edge of ourselves. So if you've ever looked up at the night sky and felt that hum in your chest, the quiet terror of realizing how small you are and how impossibly vast everything else is, then you already know why this matters. You already feel it. That pull toward the unknown, that hunger to know. You are part of this story, whether you like it or not. And the story isn't over, not even close. In the next episodes, we'll unravel the history of the universe, how humans came to map the skies, how the laws of physics turned into battlegrounds, and why the questions we ask about the universe are also questions about ourselves. This is your invitation to step into the mystery, to join the search, to wonder without shame, to stare into the dark and ask, what if there is no end? What if the universe just goes on forever? What does that do to your sense of self, your beliefs, your fears? Let's find out together. So if this spoke to you, if you felt something shift while reading this, don't let it go. Like the video, subscribe for the full journey into the mysteries of existence. And in the comments, I want to hear from you. Do you believe the universe has an edge? Or are we floating in something that never ends? This is the greatest mystery ever told, and we're telling it right here. Welcome to the edge, or whatever lies beyond. In the beginning, before mathematics was carved into clay and telescopes lifted toward the heavens, humanity looked upward, not with calculation, but with awe. The night sky was a canvas of mystery and myth, populated by gods and beasts, by stories passed through generations beside flickering firelight. Ancient people did not speak of galaxies or expansion, but of order and chaos, of balance between earth and sky. The Babylonians tracked the motion of planets with surprising precision, assigning meaning to their patterns, while the Egyptians aligned their monuments with celestial bodies, believing the stars held the secrets of the afterlife. In China, records of eclipses and comets stretch back centuries before the Common Era, and in the Americas, the Mayans crafted intricate calendars rooted in celestial cycles. Humanity's relationship with the cosmos was spiritual, philosophical, and practical, and though the language was different, the longing was the same to know what lay beyond the stars and why. It was the Greeks, perhaps, who first began to disentangle myth from mechanism, proposing that natural laws governed the heavens. Pythagoras imagined a universe built on harmony and mathematics. Plato suggested the stars moved in divine patterns, and Aristotle, though limited by geocentric assumptions, introduced the idea that the heavens were governed by different laws than Earth. Yet it was Hipparchus and later Ptolemy who would anchor the geocentric model into Western thought, with crystalline spheres and nested orbits describing a universe centered around a motionless Earth. This framework held for over 1,000 years, reinforced by religious doctrine and apparent common sense. For centuries, the stars were thought to be fixed on a dome that rotated around us, their positions unchanging, eternal. The universe was a stage, and humanity was the focal point of the divine narrative. And then, the telescope shattered the illusion. With the Renaissance came a reawakening of critical thought, and Copernicus dared to place the sun at the center, not Earth. His heliocentric model, though controversial, laid the groundwork for a cosmic reorientation. Galileo, with his primitive telescope, saw the moons of Jupiter dancing in defiance of geocentrism, and the phases of Venus revealing a truth no dogma could suppress. Kepler refined the orbits into ellipses, not circles, revealing an elegance to planetary motion, and Newton, with the stroke of universal gravitation, bound the heavens and earth with a single law. Suddenly, the cosmos was not a realm of mystery beyond reach, but a system of knowable patterns. Gravity stitched the universe together. The apple and the moon obeyed the same rules. This revelation was, seismic physics had become a key to unlock the universe itself, and as technology progressed, so too did our reach. The 19th century brought spectroscopy, revealing the elemental makeup of stars, and with it the understanding that the sun was not unique but one among billions. The faint light that reached us could be broken into rainbows of knowledge, each line a signature from across space and time. Then, in the early 20th century, came Einstein, whose theory of relativity bent the very fabric of space and time. The universe, it seemed, was not a static backdrop but a dynamic entity, expanding, curving, twisting under the influence of mass and energy. In 1929, Edwin Hubble delivered perhaps the most profound observational blow to humanity's sense of place when he discovered that distant galaxies were receding from us, their light stretched red by the expansion of space itself. The universe was growing. It had a beginning. This understanding birthed the Big Bang Theory, not as an explosion in space, but an expansion of space itself from an initial state of incomprehensible density and heat. The microwave background radiation, detected by Penzias and Wilson in 1965, served as a fossil whisper from that ancient moment, a faint echo from when the universe was just 380 years old. It confirmed what equations had suggested the cosmos was born in fire and light. But this was not a simple beginning. From the Big Bang emerged a series of mysteries as complex as the one it answered. What caused the inflationary burst in the universe's earliest moments? What is the nature of dark matter, the invisible scaffolding that shapes galaxies? Why does dark energy seem to be accelerating the universe's expansion? These questions drive modern cosmology, and they stem directly from the layered history of discovery that preceded them. In the latter half of the 20th century, humanity's eyes left Earth more literally than ever before. Spacecraft carried our senses beyond the atmosphere. The Voyager probes sailed past the gas giants and into the interstellar dark, their golden records carrying whispers of our species. Satellites mapped the microwave background in exquisite detail. The Hubble Space Telescope peered into distant galaxies, revealing that the universe was not only vast but teeming with structure, complexity, and history. Our timeline of discovery is not a smooth arc, but a series of punctuated revelations. Each telescope, each instrument, each mind built upon the last. Milestones include the launch of Sputnik, the first artificial satellite, which ignited the space race and ushered in the era of space exploration. In 1969, humanity stepped onto another world as Apollo 11 landed on the Moon, fulfilling an ancient dream and anchoring us forever as a spacefaring species. The International Space Station became a laboratory in orbit, while rovers trundled across Mars, sending back images of dusty plains and stormy skies. The Planck satellite offered a map of the universe's earliest light, while gravitational wave detectors like LIGO confirmed Einstein's predictions a century later, catching the ripples from merging black holes across the void. The James Webb Space Telescope, successor to Hubble, now stares deeper into time than ever before, witnessing galaxies as they formed billions of years ago. Each discovery redraws our maps, expands our horizons, and humbles our place. The observable universe, a concept born from this grand pursuit, refers not to everything that exists, but to everything we can see. Light has a speed, and time has passed only so long since the Big Bang. Thus, we are surrounded by a cosmic horizon roughly 46.5 billion light-years in every direction, a sphere not of borders, but of knowledge. Beyond that, the universe may stretch endlessly or curve back upon itself. We cannot know yet. What we do know is bounded by light and time. The further we look, the further back we see. Galaxies are not just points of light, but memories. The concept of the observable universe ties together centuries of human effort. It represents not just a measurement of distance, but a culmination of all the methods, tools, and minds that reached into the dark and brought back answers. It reflects the interplay between theory and evidence, between imagination and data. What began as myth beneath the stars became models in chalk and steel. The dome of the night sky cracked open, revealing not a finite stage but a vast, expanding, and possibly infinite cosmos. From Earth-centered to Sun-centered to no center at all, we have learned that the universe is not built around us, yet somehow, we are built from it. The atoms in our bodies were forged in stars. The thoughts in our minds trace back to the very beginning. This historical context is not just the story of science, it is the story of a species reaching outward, again and again, with ever clearer eyes. It is the tale of wonder sharpened into understanding, and understanding opening up even deeper mysteries. What we know today rests on the shoulders of ancient astronomers, Renaissance thinkers, modern physicists, and the boundless curiosity that threads them all together. We are part of the universe becoming aware of itself. We are not at the center, but perhaps, in knowing, we are something even more remarkable to witness. You should care not because the stars need you to, but because in some deeply human way, you've always been reaching toward them. Before you knew what galaxies were, before you had a name for gravity or expansion or time, something inside you already felt the weight of the infinite pressing softly against your thoughts. It's in the moments when the world is quiet, when you lie awake and stare at the ceiling, and suddenly remember that the Earth is spinning, that it's moving around the sun, that the sun is moving through the galaxy, and that the galaxy itself is just one in an ocean of galaxies drifting through a dark that has no edge. In those moments, the sky isn't just beautiful, it's terrifying. And beautiful again. There's something profound and uniquely human in that oscillation between awe and fear, in the way we long to understand what we cannot hold. The cosmos is not just far away, it's unknowably big. Its scale defies our instincts. When we talk about the universe, we're not talking about a place, we're talking about everything. Everything that has ever been. Everything that could ever be. And somehow, in all of that, you exist. A conscious, thinking, dreaming being made of atoms forged in ancient stars, walking on a rock that orbits a fireball that orbits the center of a spiral floating in the dark. And you care, because you're not just looking at the stars. You're looking for meaning, for connection, for a reason behind the patterns. That is what makes cosmology more than science. It's a mirror. When you learn about the observable universe, when you understand that we are surrounded by a 93 billion light-year-wide sphere of possibility, you don't feel larger, you feel small. But in that smallness, there's liberation. If we are truly that insignificant in the grand design, then maybe the beauty of existence isn't about being important. Maybe it's about being aware. Maybe it's enough to be alive in this brief sliver of time, seeing and feeling and wondering. The stars don't know your name, but you know theirs. Isn't that something? That the light from a supernova that died before humans walked the Earth can still reach your eyes? Travel across billions of years just to flicker in your sky? That the shadows of the past live above us? Always? The universe is not cold because it doesn't care. It's cold because it never promised anything. It simply is. And yet we love it. We name constellations. We make wishes on falling rocks. We send telescopes out to look farther, to find others, to hear whispers in radio waves. What kind of creature does that? What kind of creature looks at the abyss and sends poetry? The fear that comes from the vast unknown isn't just about distance, it's about truth. The more we discover, the more we realize how much we do not know. What came before the Big Bang? Is our universe just one bubble in a sea of others? Could time run backwards? Could space fold? Is reality a simulation? These are not just questions for physicists. They are questions that reach down into your gut and twist something primal. Because if we can't answer them, what does that mean about us? Are we designed to know? Are we supposed to? And yet, that fear is part of the draw. The unknown is not just a void, it's a door. And behind that door might be knowledge that transforms what it means to be human. You care because even when it's scary, you want to open it. Curiosity is not passive, it's hungry. It aches in your chest when you see the Hubble Deep Field image and realize that every point of light is an entire galaxy. It stirs something ancient when you read that the James Webb Telescope saw light that left its source over 13 billion years ago. That's not just history, that's time travel. That's a machine built by apes that climbed trees just a heartbeat ago. Now staring back to the dawn of creation. You care because it feels impossible, and yet it's real. And beyond the facts, beyond the numbers and distances and equations, there's the question that has haunted every person who has ever looked up. Are we alone? Somewhere, in a galaxy too far to reach, is there someone else staring at their night sky, asking the same question? The search for extraterrestrial life is not just a scientific mission, it's an emotional one. We're looking for family, for affirmation that we're not a cosmic accident, that someone else understands the silence we've grown so used to. The loneliness of the universe is not quiet, it's deafening. And still, we listen. SETI scans the skies. Rovers drill into Martian rock. Probes glide past icy moons. Because even a whisper would mean everything. A signal, a shadow, a structure. Anything to say we are not alone. You care because the alternative is too vast to hold. But this isn't just about aliens or black holes or origin stories. This is about you, about your life, about how knowing the scale and complexity of the universe changes the way you see everything. It alters your view of suffering, of joy, of purpose. It reminds you that every moment is rare, that consciousness is fragile, that life, yours, mine, everyone's, improbable, beyond belief. And that makes it sacred. The stars don't have to shine for you to matter, but the fact that they do, and that you're here to see them, that's enough to stop you in your tracks. When you understand the vastness of it all, you start to see the miracle in the mundane. A child laughing is a product of stardust. A tear falling is a chemical reaction birthed in a galaxy's heart. Everything you love is made of atoms that drifted through supernovae. When you see that, you can't unsee it. The cosmic perspective doesn't make life smaller, it makes it precious. You care because wonder is fuel. Because somewhere inside, the child who once looked at the stars and thought they were holes in the sky still wants to believe in magic. And, in a way, the universe gave you that. The more we learn, the stranger and more magical reality becomes. Particles that blink in and out of existence. Forces that shape galaxies but cannot be touched. Dark energy, expanding the cosmos faster and faster, like a dream unraveling. These things are not fiction. They are measured, tested, confirmed, and still they feel impossible. You care because this is the greatest story ever told, and it's still being written. You are not just an observer, you are a chapter. Your thoughts, your hopes, your questions, they are all threads in the fabric of the universe trying to understand itself. And maybe that's the most beautiful reason of all. That out of all the chaos and collisions, the stars gave rise to beings who could wonder, who could ask, who could look into the dark and say, I want to know, not because they must, but because they can. The universe doesn't owe us meaning, but we make it anyway. And that is the most human thing of all. So yes, you should care. Because when you care, you connect to the stars, to the science, to the story, and to every person who has ever looked up and felt small and loved that feeling. What if everything you've ever known, your memories, your home, your planet, your galaxy exists inside a bubble floating in an endless cosmic sea, one bubble among an infinite number? What if the laws of physics that hold your body together and keep your heart beating are not universal, but just local customs in our corner of existence? What if time isn't a straight line, but a loop, or a spiral, or something more complex than the human mind can model? What if everything you experience is a shadow cast by something far more vast, more real, that lies outside the observable edge of our universe? These aren't the questions of science fiction. They're questions rooted in real theories, backed by evidence, born from the minds of the most brilliant scientists alive today. And the reason they matter isn't just because they're mind-bending. It's because they change how we see ourselves. They ask us to step beyond comfort, beyond the known, and confront the possibility that everything we take for granted, our sense of scale, our sense of time, our place in the cosmos might be incomplete. If you've ever stared into the night sky and felt the pull of something beyond words, then you already understand what's at stake here. This mystery, this puzzle we call the universe, isn't just an academic curiosity. It's the stage on which everything plays out, from the formation of stars to the birth of thoughts in your own mind. And the more we learn, the stranger and more beautiful the questions become. Imagine waking up tomorrow to the news that we've received a clear, undeniable signal from an intelligent civilization 14 billion light years away. The message is brief, mathematical, and deliberate. It has no known source in nature. What would that do to your understanding of life? How would it change your relationships, your beliefs, your priorities? Now flip the scenario. We search for another 100 years and hear nothing. No signal, no shadow, no hint. We remain alone. What does that mean? Are we early? Are we rare? Are we a mistake? These are not trivial ideas, they are tectonic. They shake the foundations of what it means to be human. They make us question whether consciousness is a fluke or a feature, whether meaning is made or discovered. Every mystery of the universe is, in some way, a reflection of a question we hold deep within ourselves. What is life? What is death? What lies beyond the visible? What are we even capable of understanding? If the universe is infinite, then the very concept of truth might be infinite, too never complete, always unfolding. That's not a limitation, that's an invitation. To think more deeply, to ask more honestly, to explore with a kind of humility that only the cosmos can inspire. You might ask, why does this matter to me right now? Maybe you're not a scientist. Maybe you're just trying to get through your day, to make sense of your own small world. But that's exactly why this matters. The mysteries of the universe scale down. They don't just exist in equations and observatories, they exist in how we view reality. When you understand that the universe is still expanding, that the galaxies are being pulled away from one another faster and faster by a force we can't explain, it teaches you that change is constant. That movement is inevitable. When you learn that the elements in your body were created in the heart of ancient stars that exploded long before the Earth existed, it teaches you that even destruction can give birth to beauty. When you realize that the universe doesn't revolve around us, and never did, it humbles you, and from that humility comes a deeper kind of strength. A strength rooted not in dominance, but in understanding. A strength that says, I am small, but I am aware. I do not know everything, but I want to. The future of discovery lies in that desire, and what we choose to ask will shape what we find. New discoveries don't just expand our knowledge, they rewrite the rules. Think of what we thought we knew 100 years ago. The universe was thought to be static and eternal. We believed the Milky Way was the entire cosmos. Then came Hubble, who showed us that galaxies are not only other islands in space, but they're moving away from us, revealing the universe to be expanding. That changed everything. It changed cosmology. It changed philosophy. It changed theology. What happens when the next paradigm shift arrives? When we detect evidence of a parallel universe? When we confirm what dark matter truly is, or unlock the mechanism behind dark energy? When we map the edge of the observable universe and glimpse something we cannot yet name? Each of these milestones will be more than just data. They will alter how we think, how we teach, how we dream. And the best part? You get to be alive for it. You are living in a golden age of discovery, where instruments exist that can hear the collisions of black holes, that can see the afterglow of creation, that can measure the fabric of space-time itself. And yet, even with all of that, we are still just scratching the surface. So ask yourself this: what do you want to know before you die? What mystery would you give anything to see solved? Is it whether time travel is possible? Whether we are alone? Whether the universe had a creator or simply emerged from a quantum fluctuation? These are not questions to be answered overnight. They are not puzzles with easy solutions. But they are the right questions. They are the ones that draw communities together, not just scientists, but storytellers, artists, philosophers, children staring up at the sky for the first time. They are the questions that make us feel more alive, not less, and they are yours to ask. You don't need a PhD to wonder. You don't need to understand every formula to feel the thrill of possibility. The universe doesn't require your credentials, it only requires your curiosity. What would it feel like to know that everything you see in the night sky has already changed, that we see stars not as they are, but as they were? What would it mean if the present was always a shadow of the past, and the future is already written in light we have not yet seen? These aren't rhetorical questions, they're invitations. To explore, to engage, to participate in the most profound story ever written, the story of everything. And you're not alone in that pursuit. Right now, across the world, people are watching the same documentaries, reading the same articles, staring into the same skies, asking the same unanswerable things. What if you talked to them? What if we didn't treat the universe as a cold expanse, but as a shared language. Start a conversation. Ask your friends if they believe in life beyond Earth. Debate the multiverse over coffee. Imagine new worlds with your children. Share an image from the James Webb Telescope and ask someone what they feel when they look at it. The act of engaging with these mysteries creates community. It bridges divides. It brings us together in a time when we're too often pulled apart. Because no matter your background, your beliefs, your struggles vary, one looks up. Everyone wonders, and in that wondering, there is unity. So, here is your call. Stay curious. Ask the big questions. Don't be afraid to say, "I don't know," because that's where the best stories begin. Dive into the mystery not to find a final answer, but to fall in love with the process of searching. Let the scale of the universe humble you, inspire you, terrify you, and move you. Let it make your problems feel small, not so you ignore them, but so you see them in perspective. Let it teach you patience and reverence and wonder. And most of all, share that feeling. The universe is not a closed book. It's a living manuscript. And every one of us gets to write a line. What will yours say? Will it be a question no one has asked yet? A theory? A dream? Whatever it is, make it bold. Make it honest. Make it worthy of the stars. Because in the end, the universe doesn't need us to explore it, but we need to. And not just because of what we might find, but because of who we become in the searching. Far beyond the last breath of our atmosphere, past the final whisper of Earth's magnetic field, lies a silence so vast and ancient it feels like time itself is holding its breath. Space is not empty, it is woven from mystery. It stretches not as a canvas, but as a living tapestry of gravitational threads, stitched with fire, dust, and shadows. Imagine it not as black, but as layered, a place of invisible forces, unseen structures, ancient echoes, and brilliant bursts of color that human eyes rarely glimpse directly. Out there, galaxies spin like colossal pinwheels of light, some so massive they warp space around them. Others collide in slow-motion ballets, flinging tendrils of stars into the intergalactic sea. In every direction, the universe glows with stories in motion, supernovae, bursting with enough light to outshine entire galaxies, black holes twisting the fabric of reality, and regions so cold and dark that they defy detection, yet outweigh everything we can see. This is not science fiction. This is the real universe, and it is alive with awe. As your mind drifts outward into this setting, consider a single galaxia swirl of starlight known as the Sombrero Galaxy, haloed by billions of unseen stars and ringed with dust lanes where new suns are born. Each of its stars hosts the potential for planets, atmospheres, oceans, and, perhaps, eyes like yours that wonder about their place. Now zoom farther. You pass galaxies by the thousands, then millions. You enter a cluster like Virgo or Coma where hundreds of galaxies interact, orbit, merge. They pull and stretch each other, trading stars like cosmic tides. And yet even these clusters are just beads on a larger string, the great cosmic web of the universe, where galaxies align along filaments of dark matter, separated by vast void-cements expanses of almost nothing. These voids are not holes, but gaps where matter failed to gather. They are the breathing spaces between structures, larger than anything your senses can conceive, where a single atom might drift alone for centuries. Here, silence is not the absence of sound, it is a presence, a pressure, the weight of untouched time. All around, light travels across unimaginable distances, shaped by the geometry of space itself. Some light stretches into microwaves, remnants from the universe's birth, cosmic background radiation, still warming the sky with a whisper 13.8 billion years old. That radiation passes through clouds of gas and dark matter, revealing hidden shapes that only careful instruments can detect. Dark matter, though invisible, reveals itself in how it bends the path of light, a phenomenon called gravitational lensing, where entire galaxies appear warped or duplicated as their light passes through unseen mass. Dark matter is not made of atoms. It doesn't emit light or absorb it, but it holds galaxies together. It shapes the cosmos. Without it, nothing would cohere. It is the invisible scaffolding of reality, and we still don't know what it is. Then there's dark energy, perhaps the strangest phenomenon of all. If gravity pulls things together, dark energy pushes them apart. It is driving the acceleration of the universe's expansion, stretching space faster and faster over time. It accounts for nearly 70% of everything, and we have almost no idea what it's made of. We give it a name, but not a face. It behaves like nothing else we've ever observed. It is the engine behind the vastness, and it sits beyond the reach of our current understanding. In the face of such mystery, curiosity becomes a form of reverence. And yet, in this impossible immensity, human minds have dared to map, to measure, to imagine. The modern pioneers of cosmology are not explorers in the traditional sense, but their expeditions are no less bold. Edwin Hubble revealed that galaxies are racing away from us, showing that the universe is expanding. Albert Einstein offered equations that bent time and space together, predicting black holes and cosmic expansion decades before anyone observed them. Vera Rubin discovered the discrepancy in galaxy rotation speeds, which became one of the strongest arguments for the existence of dark matter. More recently, teams behind the Planck satellite and the Sloan Digital Sky Survey have mapped the early universe and the large-scale structure of the cosmos with unparalleled precision. Kip Thorne, Rainer Weiss, and Barry Barish brought us the first direct detection of gravitational waves ripples in spacetime itself. And with the James Webb Space Telescope, engineers and scientists have built a machine capable of seeing the earliest galaxies, a mirror so sensitive it can detect the heat of a bumblebee on the moon from Earth. These individuals and teams are the cosmic storytellers of our time, turning invisible forces and ancient photons into revelations that rewrite how we see the world. The atmosphere of the universe is not one of chaos, but of a deeper kind of order and order we are only beginning to decode. There is a rhythm to star formation, a timeline to galaxy evolution, a choreography to the dance of black holes. The night sky is not random, it is patterned, structured. The light we see is old. The patterns are ancient, and yet we are part of it. Our solar system orbits the galactic center once every 230 million years, meaning that the last time Earth was in this position, the dinosaurs ruled the land. The scale is not just spatial, it is temporal. The stars you see tonight are bookmarks in a story that began before Earth formed and will continue long after our sun dies. To step into this cosmic setting is to accept a certain kind of emotional gravity. It pulls on more than your mind. It pulls on your sense of meaning. You find yourself asking questions you didn't know you had. Where did this all come from? Why is there something rather than nothing? Are the laws of physics truly fixed, or do they change across different parts of the universe? Could life arise again and again, hidden in oceans under icy moons, or in clouds around red dwarfs, or in biochemical patterns unlike anything on Earth? Is intelligence a rare flicker, or a natural consequence of complexity? Every answer we find only opens new questions, and this is the joy of it. In cosmology, mystery is not a failure of knowledge, it is the fuel that drives discovery. The tone of the universe is quiet, but it is not silent. It hums with microwaves, pulses with radio waves, flashes with gamma rays and X-rays. It sings in data and in gravity. It is a concert of phenomena, most of them invisible to the naked eye, but none beyond the reach of human imagination. Scientists today build instruments that function like new senses, extending human perception into realms that were once the domain of gods. They stare into black holes not with fear, but with algorithms. They simulate the first seconds of the universe on supercomputers. They listen for the echo of inflation, trace the footprints of neutrinos, and test the boundaries between physics and philosophy. This is not dry academia. This is sacred work. This is what it looks like when curiosity becomes a method, when wonder becomes measurable. To be immersed in the cosmic atmosphere is to walk the fine line between knowledge and humility. You begin to see not just the structures of the universe, but your place within them. You are a being of carbon and water, consciousness and memory, standing on a planet that wobbles slightly on its axis, warmed by a star that is halfway through its life, in a galaxy drifting toward collision with another, in a universe that may expand forever into a frozen, starless void. And yet, here you are, thinking about it, feeling something because of it. That alone is astonishing. That alone justifies the asking, the wondering, the long nights and longer equations. In the end, the atmosphere of the universe is not something you just observe, it's something you carry with you. Once you feel the scale of it, once you understand what's out there, you never quite come back the same. You see galaxies in dewdrops, gravitational waves and ripples on a pond. You see your own life as part of a broader arc, not smaller but deeper. You realize that even the briefest human experience is entangled with the birth of stars, the expansion of space, the symmetry of physical laws. And you realize too that our instruments, our minds, our stories, they are not separate from the universe. They are the universe, waking up, reaching out, writing itself into awareness. And so, as you drift through this atmosphere of the cosmos not as a passenger, but as a participant, you come to understand something profound. You are not lost in the universe. You are woven into it. Every question you ask, every pattern you perceive, every theory you chase down the corridors of math and metaphor is part of the great unfolding. This is not just where you live. This is what you are. Star stuff, thinking about stars. Consciousness, wrapped in gravity, lit by curiosity. The universe, looking back at itself. Somewhere at the edge of everything we know, where the most ancient photons still fade across the sky, and where the furthest galaxies stretch into red so deep it borders on silence, there's a quiet, growing suspicion. We may never find the true edge of the universe. Not because we haven't tried, and not because we lack the tools, but because the edge itself may not exist in the way we imagine. The observable universe is not a wall or a shell or a boundary we might one day breach. It is a horizon painted by light, a circle carved by the finite age of the cosmos and the constant speed at which light travels. We see only what has had time to reach us, and everything beyond remains invisible, not because it's not there, but because its light hasn't arrived. We are not surrounded by emptiness, but by possibility. And yet, as far as that possibility stretches, there are signs deep, troubling signs, that our understanding may never be complete, that we may have built our knowledge atop assumptions that will one day collapse beneath their own contradictions. In chasing the edge of the universe, we have begun to see the edge of knowledge itself. The first tremors of this uncertainty came not from the sky, but from our own theories. Einstein's general relativity, beautiful and precise, tells us how gravity bends space and how time warps around mass. It predicted black holes, gravitational waves, and the expansion of space, all of which have since been confirmed. But Einstein's equations break down its singularity set, the heart of a black hole, and at the moment of the Big Bang. In these places, our math returns infinities, our logic collapses, and our predictions lose meaning. General relativity, a theory of the large, does not play well with quantum mechanics, the theory of the very small. This disconnect has haunted physics for decades. Two frameworks that work perfectly in their own domains utterly fail when forced to coexist. The universe, however, contains both black holes and subatomic particles, galaxies and quantum fields. That means somewhere, perhaps everywhere, our understanding is fractured. Somewhere, we are wrong. And the universe, as if aware of this, offers paradoxes like riddles. Quantum entanglement, in which particles separated by vast distances appear to influence one another instantly, defies locality. Time dilation, in which moving clocks run slow and gravity slows time itself, bends our intuitive sense of cause and effect. The double-slit experiment tells us particles can behave like waves until observed, suggesting consciousness or measurement somehow affects reality. And then there's the black hole information paradox. If matter falls into a black hole and disappears, where does its information go? Quantum mechanics insists information can't be destroyed. But relativity doesn't care, and somewhere in that contradiction lies a truth we do not yet have the language to express. These paradoxes are not minor glitches, they are cracks in the glass. Through them, we glimpse a deeper reality, a set of rules we don't yet understand. A cosmic architecture hidden beneath the wallpaper of our equations. Our limitations are not just theoretical. They are observational, technological, and even philosophical. We are bound by the speed of light. which means everything we see is history. Even the sun is 8 minutes old by the time its light reaches us. Distant galaxies show us how they were, not how they are. We cannot observe the present state of most of the universe. More troubling still, the expansion of space is accelerating. That means galaxies are being pulled away from us faster than light can travel. In time, most of them will vanish from our view forever. The longer we wait, the less we'll be able to see. The cosmic horizon will shrink in content, not size. Civilizations born in future eons may see a sky nearly empty, unaware that once there were galaxies in every direction. Our moment, right now, may be uniquely suited for cosmic observation. The window may be closing, and yet, we push forward. We build bigger telescopes, more sensitive detectors. We launch instruments like James Webb into space. We construct observatories like LIGO that can hear the chirp of colliding black holes. But every discovery opens new questions. The Hubble-Tensiona discrepancy between the rate of expansion measured via the cosmic microwave background and the rate measured via supernovae suggests either unknown physics or unknown error. The vacuum energy predicted by quantum field theory is 120 orders of magnitude larger than the dark energy we observe via mismatch, so severe it has been called the worst prediction in physics. These are not minor miscalculations. These are signs that something fundamental is missing, that perhaps the universe we think we know is a mirage, constructed from partial truths. Even our most cherished models contain built-in constraints. The Big Bang Theory explains the early evolution of the universe, but not what caused the bang itself. Inflation theory explains the smoothness of the cosmos, but the mechanism behind inflation remains elusive. The multiverse hypothesis, born from inflationary models and string theory, suggests an infinite number of universes, each with different laws of physics, but this remains untestable, perhaps forever outside the scope of experiment. If we cannot measure it, can we ever confirm it? And if not, is it science or metaphysics? The edges of cosmology are littered with questions that blur into philosophy. Can time exist without space? Can space exist without observers? Is mathematics a discovery or an invention? These questions are not distractions. They are warnings that the edge we seek may not be spatial, but conceptual. And then there is the human mind itself. Brilliant, imaginative, and limited. We evolved to throw spears, to navigate landscapes, to survive and replicate. Our brains were never meant to comprehend curved spacetime, quantum foam, or 10-dimensional string theory. The fact that we've managed to model black holes and map the cosmic web is extraordinary, but perhaps we've reached the horizon of what unaided cognition can achieve. It may be that artificial intelligence, or post-biological minds, will continue the search where we falter. It may be that the next great breakthrough will come from something not quite human. Or perhaps we've already glimpsed the truth but failed to recognize it, trapped by our need for metaphor, by language that bends but does not break. Even our most abstract mathematics is grounded in human perception. The universe may not speak our dialect. In this way, the search for the edge becomes a story of friction between theory and data, between imagination and evidence, between what is and what can be known, and the conflict is already underway. Every breakthrough carries the seed of the next contradiction. Every answer contains the question that will unravel it. The more we know, the more we see how little we understand. The true edge may not be a location, but a limit the boundary between what we can observe and what we can infer, between what exists and what can be proven to exist. That does not mean we should stop. On the contrary, it means the pursuit is more vital than ever. The edge may retreat as we chase it, but in the chasing, we evolve. We refine our models, sharpen our tools, and occasionally, we glimpse a new layer of reality. But we must accept the possibility that the edge is infinite, that the universe has no boundary, or that it loops back on itself in ways our geometry cannot grasp. That space is not only expanding, but stretching in directions orthogonal to our experience. That the laws we know are local, like dialects of a deeper universal grammar we cannot yet parse. This is not failure. It is a different kind of success, the kind that says our questions are finally reaching beyond our own shadow. The cosmos has never guaranteed us answers. It has only guaranteed us wonder. And in that wonder, we find something more important than certainty. We find purpose. So as we approach this conflict not with weapons, but with telescopes, equations, and dreams, we must do so with open eyes and open hands. We may never stand at the true edge of the universe. We may never find a final theory, but we will, along the way, find each other. In the shared act of asking, in the beauty of the search, in the stories we tell, as we try to hold the infinite in our minds. The universe may not resolve for us, it may not make sense in the end, but we will be changed by trying, and that is enough. The deeper we dive into the cosmos, the more we discover that the universe does not yield its secrets easily. What began as a journey of discovery guided by observations, grounded in mathematics, fueled by human wonders, becomes something far more turbulent. A struggle not just between theories, but between entire worldviews. The search for the edge of the universe, once imagined as a distant goal on the horizon, has become a battleground where foundational ideas collide. At the heart of this conflict is a simple but unresolved question. Does the universe have an edge? And if so, what lies beyond it? Yet the more we ask, the more we realize that the edge may not be a place at all. It may be a concept that breaks under the weight of paradoxes, a line that shifts depending on how we measure, from where we look, and what assumptions we make about the nature of space, time, and reality itself. The edge, in other words, is not just distant, it is elusive, and its pursuit has sparked some of the deepest tensions in the history of modern science. On one side of the conflict stands the observable universe, the region of space from which light has had time to reach us since the Big Bang. It spans about 93 billion light-years in diameter, not because the universe is that size, but because space itself has been expanding over time, stretching light as it travels. This edge is not a wall, not a border, but a limit to what we can see defined, not by physics, but by the finite speed of light and the age of the universe. It's an observational boundary, and yet we treat it like a physical one. Beyond it, the universe may go on forever, or it may loop back in on itself. Or it may be finite but unbounded, like the surface of a sphere where you can keep walking without ever falling off the edge. Complicating matters further, space is not a static container. It is dynamic, expanding, and possibly curved. General relativity allows for all these possibilities, and observations, while precise, have yet to rule any out with absolute certainty. Meanwhile, within this uncertain terrain, competing theories wage their own silent wars. Inflation theory suggests that moments after the Big Bang, the universe underwent an exponential expansion, stretching space so fast and so far that regions once connected are now forever separated. This process could have gone on indefinitely in different regions, creating a multiverse, a collection of bubble universes, each with its own physical laws. In this model, our observable universe is just one tiny patch of a much larger and possibly infinite to cosmic landscape. The idea is elegant, mathematically consistent, and supported by some aspects of cosmic microwave background data. But it also introduces complications. If the universe is infinite, how do we assign probabilities to anything? How do we test ideas about other universes we can never observe? Infinity, once a concept of mathematical beauty, becomes a philosophical and scientific challenge, pushing the boundaries of what physics can actually say. Opposing this idea, at least casting doubt, is the lack of empirical evidence. No telescope has seen beyond the observable horizon. No instrument has detected the existence of other universes. Critics argue that inflation, while powerful, explains too much, too easily. It has become difficult to falsify. And in science, a theory that cannot be tested is no longer science, it is speculation. Even string theory, which offers a mathematical framework for unifying quantum mechanics and general relativity, suggests the possibility of many universes and extra dimensions. Yet it too remains without direct experimental proof. In this environment, some physicists are calling for a return to minimalism, to theories that predict only what we can observe and nothing more. They argue that we must not let our imaginations outrun our instruments, that without evidence, we risk losing our way in the dark. But cosmology has always walked this tightrope between theory and observation. The cosmic microwave background, one of the most significant pieces of evidence for the Big Bang, was predicted before it was found. Black holes were once purely theoretical. Even the expanding universe was an inference before it was seen. So the line between science and speculation is not always easy to draw. What makes today's conflict so intense is that the stakes are higher. We are now questioning the very foundations, whether space and time are fundamental or emergent, whether our universe is unique or one among many, whether the laws of physics are eternal or contextual. These are not mere refinements, they are paradigm shifts waiting to happen. At the core of the clash is our inability to reconcile the two great pillars of modern physics. General relativity describes the smooth geometry of space and time, the curving of gravity, the motion of planets, and the structure of galaxies. Quantum mechanics describes the behavior of particles, the fuzziness of measurement, the probabilistic dance of existence at the smallest scales. But bring these two theories together in the center of a black hole, or at the beginning of the universe, and the math breaks down. Singularities form, infinities appear, equations diverge into nonsense. The search for a theory of quantum gravity, a single framework that unites the large and the smallies, perhaps the greatest unresolved quest in physics. String theory and loop quantum gravity are both contenders. Both offer hope, but both remain incomplete, untested, and fiercely debated. As cosmologists struggle to define the edge, they face another problem: language. The terms we use, beginning, boundary, expansion, curvature, carry intuitive meanings that often fail under scrutiny. If the universe is expanding, what is it expanding into? The answer, unsettlingly, may be nothing. Space isn't growing into space, it is creating more of itself. The distance between galaxies increases, not because they are flying through space, but because the fabric of space itself is stretching. This distinction is crucial and profoundly non-intuitive. Similarly, the idea of a finite universe that has no edge is difficult to grasp, yet entirely possible. We live in 3 spatial dimensions, but the math allows for higher ones. If the universe is curved through a 4th spatial dimension, we could be inside a kind of hypersphere with no boundaries, but finite volume. This is not metaphor. This is geometry, extended to the cosmic scale. The tension between infinite and finite models has never been resolved. Observational data suggests that the universe is very close to flat, its geometry neither open nor closed. But very close is not the same as exactly. We may live in a universe so large that its curvature is undetectable. Like ants on a football field, we may mistake the surface for flat simply because we haven't walked far enough. And yet, the observable universe places hard constraints on what we can know. We cannot see beyond our light horizon. We cannot receive signals from regions moving away faster than light. Even the oldest light, the cosmic microwave background, is a surface of last scattering. Before that, the universe was opaque. Our vision ends not at a wall, but in fog. And beyond that fog lies speculation, constrained only by the limits of theory. This has led to philosophical clashes within science itself. Some argue that it is time to abandon the dream of final answers, that perhaps nature does not offer a single, elegant theory, but a patchwork of effective models, valid only within certain regimes. Others insist that a deeper unity exists, waiting to be uncovered. They believe in a final theory, a theory of everything that will reconcile all forces, explain all constants, define all boundaries. But until that theory is found, we live in a fractured landscape. Observations tell us one thing. Mathematics tells us another. And sometimes they disagree. There is also a conflict of urgency. New instruments like the Vera C. Rubin Observatory and future gravitational wave detectors promise to revolutionize our view of the cosmos. But data without interpretation is meaningless, and theories without data are adrift. Cosmologists today must balance these forces, walking a line between creativity and constraint, between what is measurable and what is imaginable. It is not easy. Some days, it feels like the edge of the universe is receding faster than our understanding can chase it. Other days, a single anomalia dip in the microwave background, a strange alignment in quasar rotations suggests that something deeper lies beneath the surface. Each clue is both promise and puzzle. In this environment, humility becomes a scientific necessity. We must acknowledge that the universe does not owe us answers. It does not guarantee that its secrets are simple or even comprehensible. The edge we seek may be an illusion born of our own limitations, or it may be a feature of the cosmos we are destined to find. We do not know, and that unknowing is the conflict. It is the fire in the heart of cosmology. It is what drives us forward, even when the path bends into paradox. The tension between theories is not a sign of failure. It is the mark of a field in motion, a field alive with questions. And so we continue to search not for closure, but for clarity. Not to conquer the cosmos, but to converse with it. The edge of the universe may never be a place we reach. But in the struggle to define it, we become more than observers. We become participants in the great unfolding. The conflict is real. It is unresolved. And it is, perhaps, the most beautiful part of the journey. What if the universe has no edge? Not because it's hidden or distant or just out of reach, but because it fundamentally doesn't exist. What if space has no boundary, no ending wall, no cosmic perimeter we might one day pierce with our most advanced telescopes or theoretical equations? What if the universe is infinite in every direction, stretching beyond time, beyond comprehension, not into more space, but as space itself, unfolding in patterns we are only beginning to trace? This is not just a scientific possibility. It's a reality many physicists now consider likely. And if it is true, then the consequences are not just technical, they are transformative. The implications reach into the heart of physics, into the architecture of cosmology, into the very nature of our existence. Because a universe without an edge is a universe without a center, without a privileged position, without finality. And that changes everything. First, the implications for physics are monumental. An infinite universe means we cannot measure everything, only what lies within our observable horizon. It means that every law of nature we believe to be universal might only be locally valid. The constants we take for granted, the speed of light, the strength of gravity, the mass of the electron, could be fixed only within our visible bubble, varying across distances so vast that light hasn't had time to cross them. In an infinite cosmos, our observable patch becomes a statistical sample, not a universal truth. That forces physicists to rethink the meaning of a law. Are the laws of physics truly foundational? Or are they emergent, like the properties of water arising from molecular behavior, true within a system but not dictated from above? This redefinition reshapes how we frame our theories, how we build models, how we interpret every equation written on chalkboards and simulated by supercomputers. If the universe is infinite, then so are the possibilities, and that forces science to confront the limits of its method. Because in an infinite cosmos, some things may never be provable for lack of intelligence, but for lack of access. It also demands a reevaluation of cosmology. For decades, cosmologists have tried to reconstruct the universe's story from the Big Bang to now mapping its expansion, measuring its age, simulating its fate. But all those efforts are confined to what we can see. The cosmic microwave background, the oldest light in the universe, forms a kind of boundary around our knowledge, a glowing shell from when the universe became transparent 380 years after the Big Bang. Everything before that is hidden in opacity, and everything beyond our current light horizon is hidden in time. If the universe has no edge, then our maps will always be incomplete. No matter how advanced our instruments become, there will always be regions of space we cannot observe, not because they are too small or too dark, but because they are receding faster than light can reach us. The universe is expanding, and that expansion is accelerating, driven by dark energy. Eventually, most galaxies will disappear from our view. Stars will fade. The cosmos will become more empty, not because it ends, but because it escapes. A universe without an edge is also a universe where we may lose contact with almost everything we currently study. Our cosmic isolation will grow. Our maps will shrink. And yet, the greatest impact may not be scientific. It may be philosophical, existential. Because an infinite, edgeless universe forces us to ask, what does it mean to exist when existence has no boundary? If there is no edge, then there is no Outsideno beyond the universe. All that is here. That alone is staggering. But it also implies that all configurations of matter that can happen will happen somewhere, sometime, repeated endlessly across an endless cosmos. There may be another Earth, another solar system, another you, reading these same words in a room that looks exactly like this one. Not in some parallel universe, but somewhere far enough away that the odds repeat. It sounds absurd, but mathematically, in an infinite universe, it becomes a certainty. Every possibility happens not once, but infinitely. That is not a comforting thought. It is a destabilizing one. It makes reality feel less like a narrative and more like a pattern. Less like a journey, more like a lattice. What does identity mean in such a universe? What does choice mean? If there are infinite versions of you making every possible decision, then what defines the self? Are we just one node in a vast web of possibility, no more significant than a drop in a boundless sea? This is where physics merges with philosophy, and where science becomes introspection. For thousands of years, humans believed the universe revolved around the Earth. Then we learned we were orbiting the Sun. Then we learned the Sun was one of many in the Milky Way. Then we learned the Milky Way was one galaxy in a sea of billions. And now, perhaps, we learn that even our entire visible universe is just one region of an infinite cosmos. At each stage, we've been forced to let go of specialness, to release the illusion that we are the center, that we are singular. And yet, in doing so, we've found something deeper, not significance through location, but significance through awareness. The universe may not be made for us, but we are part of it. We are made from its materials, bound by its laws, driven by its energies. And in a universe without edges, that connection is endless. The atoms in your body were forged in stars that exploded billions of years ago. Those atoms will one day become something else. The cycles continue. There is no edge. This perspective demands new physics, not because what we know is wrong, but because it is incomplete. Quantum mechanics, general relativity, the Standard Model, all of these are extraordinarily successful. They have predicted particles, measured forces, and launched spacecraft with incredible accuracy. But none of them answer the biggest questions. Why these laws? Why this universe? What came before the Big Bang? Is there such a thing as before? A universe with no edge forces us to expand our conceptual toolkit. It pushes us toward unification not just of theories, but of understanding. Physicists are already seeking these deeper models. Quantum gravity, loop theory, holographic principles. The idea that space and time are emergent rather than fundamental, all of these are attempts to peer beyond the current framework. But each step forward reveals more complexity. The closer we come to understanding, the more we realize how much we don't know. An edgeless universe is not only vast in space, it is vast in possibility. And that demands humility. We must be willing to accept that the final theory may not look like anything we expect. It may not be elegant, it may not be beautiful, it may not even be complete. And so we return to the human level, not the scale of galaxies or inflation, but of individuals asking why. In a universe with no edge, the search for meaning does not end. It deepens. We do not ask less way, ask more. How should we live in a reality that has no boundary? What does purpose mean in a cosmos without a goal? These are not scientific questions, but they are scientific consequences. The story of the universe is the story of us. Not because we are central, but because we are aware. And that awareness is rare. Perhaps not unique, but still astonishing. In a universe of particles and fields, we are something else, something that looks up, asks questions, dreams. That may be the greatest implication of all. Not that the universe has no edge, but that in such a universe, wonder still survives. The conflict that led us here between models, between observations, between infinities, was never a mistake. It was a necessary fire. It burned away illusions. It forced us to grow. And now, standing at the end of what we can know, we face the beginning of what we cannot. That edge, the edge of understanding, is always moving, always shifting. And that is what makes this journey worthwhile. Not the destination, but the pursuit. Not the edge, but the unfolding. We may never find the end of the universe, but we will never stop reaching for it. Because to be human in an edgeless cosmos is to be a question, a flame, a thought that stretches with the stars. And in that stretch, we find the closest thing to truth we may ever know. There comes a moment in every journey, every story, every discovery where the momentum shifts, where the mystery deepens, not because we've found nothing, but because we found too much. The universe, once assumed to be simple in its vastness, turned out to be a layered machine of forces and fields, each deeper than the last. And in the search for the universe's edge, the turning point came not with a single telescope, not with a single theory, but with a series of revelations that fundamentally changed our understanding of space, time, and the fate of everything that exists. What began as a quest to chart the stars became a confrontation with something far stranger, something invisible, unstoppable, and woven into the structure of the cosmos itself. That something is called dark energy. And its discovery marked the most important shift in cosmology since the Big Bang Theory itself. At the close of the 20th century, two independent teams of astronomers set out to measure how fast the universe was slowing down. That's what they expected, after all. Gravity pulls things together. Over billions of years, the expansion that began with the Big Bang should have been decelerating. The universe, having burst outward from its singular origin, should have been coasting, dragging its galaxies through a thickening web of gravitational resistance. The only question was, how fast was that deceleration happening? But what they found was not just unexpected, was world-shattering. The universe wasn't slowing down, it was speeding up. Something was pushing galaxies apart faster and faster, accelerating the expansion of space itself. That force, whatever it was, had to be incredibly weak, undetectable in our daily lives, but also incredibly dominant on cosmic scales. It came to be known as dark energy, and it now accounts for nearly 70% of the energy content of the universe. This revelation was the pivot point. From that moment on, cosmology wasn't just about galaxies and radiation, it was about the structure of reality itself. Dark energy didn't just challenge our understanding of the universe's expansion, it challenged the very idea of the future. If dark energy remains constant or even grows stronger, the universe will expand forever. Galaxies will drift so far apart that their light will never reach each other. Star formation will cease. Black holes will evaporate. Everything will dissolve into a cold, empty void, the so-called heat death of the universe. In that future, even time itself may lose meaning, but dark energy is not well understood. It may not be constant, it may change, it may even reverse. We don't know. And that's the frightening beauty of it. The fate of the cosmos hinges on something we can barely define, something we didn't even know existed until a few decades ago. The turning point was also driven by technology, by the machines we built, to see what our eyes never could. The Hubble Space Telescope, launched in 1990, became more than a tool. It became a witness. Floating above Earth's atmosphere, it sent back images that transformed how we imagined the universe. The Hubble Deep Field, in particular, changed everything. It was a gamble. Point the telescope at a patch of sky, so empty it seemed to contain nothing. No stars, no galaxies, just darkness. But when the long exposure completed, the darkness exploded into thousands of galaxy spirals, ellipticals, glowing smudges frozen in time. Every dot was not a star, but an entire galaxy, some over 10 billion light-years away. It was a photo of the distant past, of light that had traveled since before our sun existed. In a single frame, we saw the vastness not as a number, but as an image, infinity, suddenly visible. This image, and the data that followed, proved something profound. the universe was far more structured and far more complex than we had imagined. Galaxies weren't randomly scattered. They clustered along filaments of invisible mass, tracing a cosmic web shaped by gravity and, perhaps, by dark matter. This hinted at something else, that the visible universe was only a sliver of what exists, that most of what defines the universe cannot be seen, only inferred. This wasn't metaphor, it was measurable. Gravitational lensing showed us how massive objects warped the light around them, revealing the presence of mass that emitted no light. Dark matter, a silent architect. And yet, even dark matter is not enough to explain the behavior of galaxies on the largest scales. There is something else. Some deeper field, some hidden pressure, some energy that lives in the vacuum itself. That is dark energy. And then came the Planck Satellitea mission to map the cosmic microwave background with higher precision than ever before. It measured the leftover radiation from the Big Bang, a baby photo of the universe, when it was only 380 years old. What it showed was both expected and deeply unsettling. The fluctuations in the early universe matched our models. The geometry appeared flat, or very close to it. But there were anomalies, cold spots, unexplained alignments, statistical oddities that could be noise or could be signals from beyond our observable bubble. Planck's data gave us the best estimates yet for the universe's composition, age, and shape. But it also raised questions that remain open. Questions about inflation, about the nature of the early universe, about whether we live in a special patch of the cosmos or whether something stranger, something multiversal, lies beyond the edges of our vision. Most recently, the James Webb Space Telescope has opened an entirely new window. With its powerful infrared vision, it peers not just far away, but far back in time, capturing light from the first galaxies ever formed. And already, it has found surprises. Galaxies too large, too bright, too organized for their age. Structures that shouldn't have had time to form under our current models. These observations have begun to shake the foundation of our understanding of the early universe. Are our models wrong? Is there something fundamental we're missing about how matter clumps, how stars ignite, how galaxies evolve? These are not small tweaks. These are the early signs of a paradigm shift, a turning point in progress. But perhaps the most powerful shift is not in the details in our attitude. The turning point is about realizing that the universe is not built to be understood easily, that every answer reveals a deeper question, that the edge we search for may not be spatial, but conceptual, that we are not just charting space, we are charting reality. The edge of the universe may be the edge of our models, the edge of our language, the edge of thought itself. And in that realization, something changes. Science becomes not just a method, but a mindset, a reverent curiosity, a commitment to never settling. We used to think the edge was a placia point on a map. Now, we know better. The edge is an idea, one that moves as we move, one that refuses to stay still. Every telescope we launch, every particle we detect, every simulation we run pushes it back a little further, but it's always just ahead of us, like a mirage. That's not defeat, that's discovery. Because the goal was never to find the end. The goal was to understand the beginning, and maybe, just maybe, to understand ourselves. So here we are, in the wake of revelations that rewrote the rules, in a universe filled with invisible matter, driven by unknown energy, expanding faster than we ever thought possible, in a universe that has no center, no edge, and possibly no end. And we are watching it, mapping it, questioning it with machines in orbit, detectors underground, minds across the world lit by the same wonder that drove the first astronomers to look up. The turning point has already come. We are living in it, and what comes next depends on how deeply we dare to ask. For most of human history, we have looked outward to understand the universe. We charted the stars, mapped the skies, built telescopes to pierce deeper into the void, all in the pursuit of that elusive, edgesome final border where the known meets the unknown, the finite gives way to the infinite. But what if we've been looking at the problem the wrong way? What if the edge we seek is not out there in space, but somewhere entirely different in the structure of reality itself, in the assumptions we carry, in the way we define space, time, and information. In recent years, a quiet revolution has been taking place at the heart of physics and cosmology, one that challenges not just the content of the universe, but its very framework. At the center of this revolution are ideas so radical, they seem like science fiction. Yet they are grounded in real math, real experiments, and real paradoxes. Ideas like the holographic principle, which suggests that everything we experience as three-dimensional might actually be encoded on a two-dimensional surface. Ideas that say space is not fundamental, but emergent. That time itself may be an illusion. That the universe, far from being a vast arena we move through, might be a quantum projection and image created not by light, but by information. It began with a puzzly simple one, at least on the surface. What happens to information when it falls into a black hole? According to general relativity, the matter is crushed at the singularity, the point of infinite density. According to quantum mechanics, information cannot be destroyed, ever. And so, physicists were left with a contradiction. If black holes destroy information, then quantum mechanics is wrong. If they preserve it, then general relativity is incomplete. For decades, the brightest minds wrestled with this paradox. Stephen Hawking famously argued that information was lost forever. Others disagreed. But then, a stunning idea emerged. What if the information isn't inside the black hole at all, but on its surface? Not trapped within the volume, but encoded on the event horizon, the boundary beyond which nothing can escape. This was the birth of the holographic principle, first proposed by Gerard 't Hooft and later formalized by Leonard Susskind. It drew from earlier work in string theory and thermodynamics, which showed that the amount of information or entropy that a black hole can contain is not proportional to its volume, but to its surface area. That is, the content of the black hole depends on how big it appears from the outside, not how much space it occupies. And if that's true for black holes, why not for the universe itself? What if everything we experience as space, objects, ourselves, not encoded inside a volume, but on some cosmic boundary? What if reality is a hologram? In such a model, the three-dimensional world we inhabit is a projection from a two-dimensional surface, a kind of cosmic screen we cannot see. It sounds absurd. And yet, it solves problems that traditional models cannot. It reconciles gravity with quantum mechanics. It explains black hole entropy. And it suggests that space itself, the very thing we are trying to map, may not be fundamental. It may be an illusion, created by deeper, non-spatial information patterns. That's not just a change in content. That's a shift in perspective. And the shift doesn't stop there. Other theories suggest that time, too, is emergent, not a flowing river, but a statistical property of quantum entanglement. That what we experience as the arrow of time is not a basic feature of the universe, but a side effect of how systems interact, decohere, and evolve. In some models of quantum gravity, space and time dissolve into networks of relationships qubits, entangled across abstract graphs, giving rise to the geometry of the universe only at large scales. In this view, there is no where or when at the deepest level. There are only correlations, patterns, entanglements, and out of these, the illusion of a universe arises. This isn't metaphor. This is mathematics, and it's being tested right now in laboratories and observatories around the world. What drives this shift in perspective is the realization that many of the universe's deepest mysteries resist explanation within the classical framework. Why does the cosmological constant, the energy of the vacuum, have the value it does? Why does the speed of light limit information transfer? Why do particles obey specific statistics? These are not random features. They are clues. And when examined from the quantum perspective, they start to make sense not as isolated facts, but as emergent phenomena from a deeper substrate. Quantum mechanics, with its bizarre counterintuitive rules, is not just a set of equations. It is the scaffolding of reality. And within that scaffolding, space and time may not be ingredients. They may be results. This changes how scientists talk about the edge of the universe. If space is emergent, then the idea of an edge may be meaningless. You cannot find the boundary of an illusion. If the universe is a hologram, then our attempts to measure the farthest galaxy may be like trying to find the edge of a movie screen by crawling into the scene. We are inside the projection. We are part of it. And the true structure lies somewhere else, not in another place, but in another description. The shift is not about replacing science with speculation. It is about recognizing that our frame of reference may be wrong. And throughout history, such shifts have always been painful. When Copernicus suggested that the Earth orbited the Sun, it wasn't just an astronomical correction, it was a philosophical revolution. When Einstein replaced Newton's absolutes with the relativity of space-time, it wasn't just new math, it was a new way to think about motion, light, and time. Now, we may be facing another revolution where even the concept of place breaks down, one where reality is not made of things in space, but of information organized in layers we have only just begun to uncover. And here's where quantum mechanics becomes more than a theory, it becomes a language. Because the universe, at its smallest scales, does not behave like a machine, it behaves like a process. Particles are not objects, but excitations of fields. Their properties are not fixed, but probabilistic. Their behavior depends on observation, interaction, and context. And when you scale these ideas up, you begin to see the universe not as a static arena, but as a dynamic computation. A feedback loop of cause and effect, of entangled possibilities, of probabilities collapsing into events. Space becomes a tapestry woven from relationships. The edge becomes not a wall, but a limit to coherence. A place where patterns fail, not because they end, but because they cease to be meaningful. This is not to say that everything is solved. Far from it. These are early days. The holographic principle is still theoretical, with key models based on ad space, anti-de Sitter, rather than our universe's apparent de Sitter geometry. The emergent models of space-time remain speculative, with mathematical beauty outpacing experimental proof. But the shift in thinking is real. It is already influencing how we build theories, how we interpret data, how we design experiments. Physicists no longer speak of the universe as a machine, but as an interface. A system that responds, that adapts, that hides its deepest rules behind patterns we mistake for structure. And in that shift, something extraordinary happens. We stop trying to reach the edge. We start trying to decode the projection. This new perspective also opens doors for unity. Quantum mechanics and general relativity, long in tension, may be reconciled not by brute force, but by rethinking the assumptions that keep them apart. If space and time are emergent, then gravity itself may be Entropica's statistical effect of deeper informational laws. This idea, explored by physicists like Eric Verlinde, suggests that gravity is not a fundamental force, but a thermodynamic side effect like pressure in a gas or temperature in a crowd. That's a profound change. It means our most basic intuitions about weight, motion, orbits may all be consequences of something else, something hidden, something digital. And if that's true, then the universe is not just physical, it is computational. All of this points to a single, breathtaking possibility: that we have been asking the wrong question. The edge of the universe is not a place we haven't reached. It is a concept we haven't redefined. And redefining it requires more than technology. It requires imagination. It requires humility. It requires the courage to say, we might be wrong not in our measurements, but in our metaphors. Not in our data, but in our diagrams. And from that courage, new science is born. We are at a turning point. The theories we build now will shape how the next generation sees the cosmos. The questions we ask today will echo into the next century. And the shift we are experiencing from space as substance to space as code, from time as flow to time as correlation, from matter as object to matter as information is not a retreat from reality. It is a deeper embrace. Because to understand the universe, we must go beyond looking. We must start listening to the math, to the contradictions, to the whisper of symmetry breaking under its own weight. So here is where the real journey begins. Not at the edge of the universe, but at the edge of perspective. A place where old ideas dissolve and new ones rise. A place where space is not the final frontier, but the first illusion to fall. It was supposed to be simple, at least by cosmological standards. The universe, born in fire, expanding in space, governed by physics. We were to map it, understand its laws, chart its boundaries, and someday stand at its edge. That was the idea, the noble vision that drove centuries of science. But something unexpected happened along the way. As our telescopes reached further, as our theories grew bolder, the fabric of the universe began to behave strangely. It flickered with inconsistencies, echoed with patterns we couldn't explain, and opened doors into possibilities that shattered the very frame of what we thought the universe was. Suddenly, the edge we were chasing began to shift not away from us in space, but inward, into the deepest layers of reality. And what we found there wasn't a wall. It was a question so profound it reframed everything. What if the universe is not the only one? What if it's not even real in the way we think it is? The first clues came wrapped in paradox. The fine-tuning of physical constants, the precise values of the strong nuclear force, the mass of the electron. The strength of gravity, all balanced so delicately that even the slightest change would render the universe uninhabitable. For years, physicists wrestled with this improbable balance. Why does the universe seem built for life? Why does it even exist at all, instead of collapsing into chaos? The more we measured, the more it seemed as though we were standing in a cosmic showroom, everything tuned just right, down to the decimal, to allow galaxies, stars, planets, and people. And that raised a possibility many were reluctant to confront. Maybe we're not in the only universe. Maybe there are countless other seats with different laws, different constants, different outcomes. Maybe we live in this one not because it's special, but because it's one of the few where beings like us could even exist to ask the question. This was the beginning of multiverse theory. Not a single idea, but a family of them. There's the cosmic inflation multiverse, where inflation didn't stop everywhere at once, but in patches, bubbles, each forming its own universe. There's the quantum multiverse, where every possible outcome of every quantum event actually happens, splitting reality into a web of branching worlds. There's the string theory landscape, which suggests 10 QA possible solutions to the equations of reality, a different kind of universe, with different particles, different physics, different dimensions. These are not metaphorical. They are mathematical consequences of our best theories. And though we can't observe them directly, their logic is inescapable. If these models are right, then our universe is not the universe. It is a universe. One thread in a cosmic tapestry so vast and varied that the idea of an edge becomes meaningless. Because how can there be an edge to something that is one of infinite variations? What lies beyond our universe might not be more space, it might be more universes. And just when that idea began to sink in, when scientists started to cautiously entertain the implications, a new, even more unsettling theory emerged. One not from astronomy, but from information, theory, and computer science. What if the universe isn't real at all, not in the way we think? What if it's a simulation? This hypothesis, long considered fringe, began to gain traction among serious thinkers. It began not as a conspiracy theory, but as a logical outcome of exponential technological growth. If civilizations can survive long enough to develop planet-scale computing power, if they can simulate minds, environments, and histories indistinguishable from real experience, then the number of simulated realities could vastly outnumber base reality. In such a scenario, statistically speaking, we are more likely to be inside a simulation than outside one. That's the unsettling argument proposed by philosophers like Nick Bostrom. And while we have no proof, some physicists are beginning to ask, could we test this? Could reality have a resolution limit, like pixels? Could space be granular, like code? Could quantum uncertainty itself be the result of computational shortcuts? The implications are staggering. If the universe is a simulation, then everything we see, the stars, the galaxies, the laws of physics could be part of a rendered environment. The Big Bang could be a boot-up event. The cosmic microwave background. a loading pattern. Dark matter, an artifact of underlying code. In this model, the edge of the universe is not a spatial boundary. It's a programmatic limit, the point at which rendering is no longer necessary, because no conscious observer exists to perceive it. That's not science fiction anymore. It's a real philosophical position being discussed in scientific circles. And it raises the most profound question yet. If we are simulated, who or what is running the simulation? But maybe the truth is even stranger. Maybe the universe is not simulated. Maybe it's not alone. Maybe it's not built on particles or waves, but on information itself. In recent years, more and more physicists have begun to speak of the universe not as a collection of things, but as a process of computation. Every interaction is an exchange of information. Every particle, a bit of data. Every law of physics, a rule in a universal program. This is not metaphor, it's math. The black hole information paradox, the holographic principle, the entanglement entropy of quantum field Sol suggest that information is more fundamental than matter. That the fabric of the cosmos is not made of stuff, but of code. And if that's true, then the edge of the universe is not where matter ends, it's where meaning begins. This shift in perspective doesn't erase the mystery, it deepens it. Because if the universe is information, then consciousness is no longer an afterthought. It becomes central. Awareness is not a fluke of biology, it's part of the system. Entanglement, observation, measurement all point to a strange intimacy between mind and matter. In quantum mechanics, particles do not have definite properties until measured. In cosmology, the observable universe depends on the position of the observer. Maybe this isn't coincidence. Maybe the universe is not a machine that created consciousness. Maybe consciousness is part of what creates the machine. And that idea leads us to a place even science rarely dares to go: a cosmic self-awareness. Could it be that we are not separate from the universe, but an expression of it? That we are not outside observers, but participants in a loop of awareness that reflects itself across scales and systems? That the universe is trying to understand itself, and we are the mechanism? Carl Sagan once said, "We are a way for the cosmos to know itself." He meant it poetically. But what if it's literally true? What if every question we ask, every mystery we chase, every map we draw is not about reaching the edge, but about turning the universe inward? What if the twist is that we were never meant to find the edge? Because the edge doesn't exist in space. It exists in us. This is the unexpected twist. That the universe is not what we thought. That the questions we've been asking are not just scientific, they're existential. That the edge we've searched for is not a place, but a threshold, a moment in understanding where everything changes. From galaxies to code, from particles to patterns, from space to thought. And in that realization, everything becomes connected. The Big Bang becomes more than an event, it becomes a story. The cosmic web becomes more than a structure, it becomes a language. And the dark, endless sky becomes more than a void. It becomes a mirror. So here we are, not at the edge of the universe, but at the edge of knowledge. What lies beyond cannot be seen not yet, but it can be imagined. It can be theorized. It can be felt. We don't need to break through the cosmic horizon to understand our place. We are already woven into it. We are the question the universe is asking itself. And perhaps, just perhaps, we are also part of the answer. We stand now on the shoulders of 1,000 discoveries, the edge not of space, but of insight staring deeper into the fabric of the cosmos than any generation before us. We've seen the birth of galaxies, detected the collision of black holes, mapped the afterglow of creation itself. We've unlocked strange forces like dark energy, contemplated impossible scales, and dared to imagine an infinite, edgeless universe. And yet, for all we've uncovered, we are surrounded by questions we cannot yet answer, constrained not by a lack of curiosity, but by the limits of our technology, our models, and even our perspective. The new challenge is not just to push forward, it is to break through. First, and perhaps most pressing, are the limitations of our observational reach. Every telescope, every satellite, Every detector we've launched into orbit or buried in the Earth is a marvel of human engineering. But they are still blind to most of the universe. We observe only the electromagnetic spectrum, the light emitted by stars, galaxies, and gas butt. This light makes up a tiny fraction of what's really out there. The visible matter we detect accounts for less than 5% of the total mass energy content of the universe. The rest, dark matter and dark energy, is invisible, unobservable by traditional means, and only inferred by the effects it has on things we can see. We are, in the most literal sense, studying the universe through shadows. And to move forward, we must learn to see the invisible. To do that, we need new instruments, ones that can go beyond light. Telescopes like the James Webb Space Telescope are already pushing boundaries by peering into the infrared, revealing galaxies from the dawn of time. But even Webb is limited by wavelength, resolution, and time. What we need next are observatories that can see gravitational waves across the cosmos, not just from rare dramatic mergers, but from the quiet ripples of the early universe itself. Projects like LISA, Laser Interferometer Space Antenna, promise to do just that. 3 spacecraft in a triangular formation, orbiting the Sun, measuring the fabric of space-time across millions of kilometers. With LISA, we may one day hear the Big Bang directly, unlocking a part of the universe we've never been able to access. We also need better tools to map the distribution of dark matter. Though we cannot observe it directly, we know it exists because of how it bends light gravitational lensing. But current instruments only provide coarse, large-scale maps. The next generation of missions like the Euclid Satellite, ESA, and the Nancy Grace Roman Space Telescope, NASA, are designed specifically to map dark energy and dark matter more precisely, charting how cosmic structures have evolved over billions of years. These missions will give us a finer view of the cosmic web, the vast network of filaments that connects galaxy clusters and stretches across the universe. But space-based technology isn't the only challenge. Earth-based observatories, too, are pushing the edge, like the Vera-C Rubin Observatory, which will conduct the Legacy Survey of Space and Time, LSST, producing the largest movie of the night sky ever made. With it, scientists will track billions of objects in real time, catching everything from near-Earth asteroids to the subtle wobbles of cosmic expansion. Rubin will also help us address a growing problem in cosmology: the Hubble-Tensiona disagreement between the rate of cosmic expansion predicted by early universe measurements and the rate observed in the nearby universe. This isn't just a measurement error, it could be a sign of new physics, and we need more data to know for sure. Of course, data is only half the battle. Once collected, it must be analyzed. And the sheer volume of information now being gathered, petabytes of raw measurements, is too vast for traditional methods. This is where artificial intelligence and machine learning come into play. AI can recognize patterns humans might miss, simulate alternative universes, and refine theoretical models against complex, noisy data. But even AI has limits. It needs better models, grounded in physics, to produce meaningful insight. And so, the challenge becomes a fusion of disciplines. Computer science, theoretical physics, and cosmology must work together, or risk collapsing under the weight of complexity. But even as we build better instruments and smarter algorithms, we run into a deeper problem: cosmic horizons. The observable universe is bounded by the speed of light and the age of the cosmos. No matter how advanced our tools become, we cannot see beyond this horizon. Light from farther away simply hasn't had time to reach us. And as the universe expands, more and more galaxies will slip beyond this horizon, never to be seen again. Eventually, all we'll see is a shrinking island of stars surrounded by darkness. If we want to understand the true shape of the universe, its topology, its size, its boundary, or lack thereof, we need new kinds of physics. Physics that can make predictions without direct observation. That means developing testable models of quantum gravity, of emergent space-time, of holographic universes. These are not mere theories, they are now necessities. Another major hurdle is precision. Cosmology today is entering what scientists call the era of precision cosmology, where we know the shape of the universe to within a fraction of a percent, the age of the universe within tens of millions of years. and the makeup of matter and energy to 3 decimal places. But these precise numbers hide deep confusion. They raise questions about the flatness problem, the horizon problem, and the cosmological constant problem, each a riddle that points to something we've missed. If our measurements are correct, then our assumptions must be flawed. And the only way to resolve this is to build new physics from first principles, to ask, what if space and time are not fundamental? What if they emerge from quantum entanglement, from information theory, from thermodynamics? What if our whole concept of universe is incomplete? This is not an easy path. These ideas live at the intersection of science and philosophy. They are hard to test, harder to measure, and often resist intuitive understanding, but they are necessary. Because the most profound questions about the origin of the universe, the nature of dark energy, the structure of reality itself will not be solved by building bigger telescopes alone. They require a conceptual revolution, a shift in how we frame problems, not just how we solve them. Still, despite all the challenges, scientists remain relentlessly optimistic. Every new discovery begins with a question we weren't equipped to answer. And every paradigm shift has come from a problem we couldn't ignore. When Galileo first turned his telescope to the sky, he didn't know he was about to upend centuries of thought. When Einstein rewrote space and time, he did so because the math of Newton couldn't explain the motion of Mercury. When LIGO heard the first gravitational wave, it was the result of decades of theoretical groundwork, engineering grit, and sheer belief in the impossible. Now, we stand at a similar crossroads. The tools are ready, the questions are sharp, and the future is calling. The next generation of space missions will launch within our lifetimes. We will send probes beyond the solar system. We will build quantum sensors that detect fluctuations in the vacuum. We will run simulations of the entire early universe on exascale computers. And eventually, inevitably, we will look back on this era as the moment when the edge of the universe shifted from a frontier into a framework. Because that's what science does. It takes what we thought was a limit and turns it into a lens. It shows us that the unknown is not a wall, but a mirror. And in that mirror, we see the next generation of explorers armed with questions, powered by tools we haven't yet built, and driven by the same ancient fire that first made humans look up and wonder, what's out there? How far does it go? And what lies beyond the edge? The answers are coming, but they won't come easily. They will be earned through challenge, through patience, and through a relentless refusal to stop asking. The universe is not done revealing itself, and neither are we. The search for the edge of the universe has always been more than a physical journey. It's a confrontation with the deepest limits of knowledge. With each advancement in observation, each refinement of theory, each new particle detected or gravitational wave heard across space-time, we are drawn closer to a line that never quite resolves. For decades, scientists believed that line would eventually reveal a final frontier, a literal edge, or at least a boundary condition that would bring the universe's vast complexity into focus. But as we cross into the 21st century's most sophisticated models and data-rich observations, what we found instead is a universe that reflects back contradiction, ambiguity, and paradox. The final confrontation is here not between humanity and the edge of the cosmos, but between the competing ideas that claim to describe it. These are not amateur theories or fringe beliefs. They are serious frameworks grounded in rigorous mathematics, experimental reasoning, and data from instruments we could only dream of a century ago. But they disagree. And in their disagreement, we find the central drama of modern physics. At the core of this confrontation lies the most persistent divide in science, the failure to reconcile general relativity, Einstein's beautiful theory of the very large with quantum mechanics, or strange, probabilistic theory of the very small. Relativity works flawlessly when describing the curvature of space-time, the behavior of planets, the expansion of galaxies. Quantum mechanics, on the other hand, governs the micro-universe with mind-bending accuracy, explaining atomic interactions, particle behavior, and quantum entanglement. But bring these two frameworks together into black holes, or the instant after the Big Bang, and they collapse into mathematical chaos. Their equations become incompatible, their principles contradict each other. For decades, This rift has haunted theoretical physics, and now, at the edge of cosmological understanding, it threatens to split the future of science itself into competing paths. One of the most ambitious of these paths is string theory, a framework that proposes that all particles are not point-like dots, but tiny vibrating strings. These strings resonate at different frequencies to produce the different particles we observe. Elegant, multidimensional, and unifying, string theory offers a tantalizing solution to the rift between gravity and quantum physics. It weaves the known forces into a single mathematical language and suggests the existence of multiple dimensions beyond the familiar three of space and one of time. But its weakness is a profound one: lack of experimental verification. For all its mathematical grace, string theory has yet to produce a testable prediction. Its critics argue that it may be more philosophy than physics, an elegant castle built on unobservable foundations. In contrast, loop quantum gravity, LQG, tackles the problem from a different angle. Rather than trying to embed gravity into a quantum field theory, LQG begins by quantizing spacetime itself. It suggests that space is not continuous, but made of discrete loops, tiny quantum grains of geometry, like pixels in the fabric of reality. These loops weave into a dynamic structure that gives rise to gravity as an emergent phenomenon. Unlike string theory, LQG makes fewer assumptions and doesn't require extra dimensions. Its strength lies in its conceptual clarity. But it too faces major challenges, namely, connecting its mathematical structure with known particles and forces, and making predictions that can be tested in experiments. Hovering over both these approaches is the specter of the multiverse, a consequence of inflationary cosmology, string landscapes, and quantum branching. If these models are true, we may live in just one of countless universes, each with different physical constants, laws, even numbers of dimensions. This idea has explanatory power. It helps resolve the fine-tuning problem, the puzzle of why our universe appears perfectly calibrated for life. But it also raises philosophical challenges. If other universes are unobservable, are they scientific? Can something that cannot be measured still be considered physics? The debate is fierce. Some cosmologists argue that multiverse theories push the boundaries of testability too far. Others insist that science must follow the logic of theory, even into the unobservable, if that's where the math leads. Then there are emerging models that challenge our very framework of reality. The holographic principle, which originated in black hole physics, proposes that all the information contained in a volume of space can be described by information on its boundary, much like a hologram. If true, the three-dimensional universe we perceive might be a projection of more fundamental two-dimensional data. This radical view, supported by calculations in string theory and black hole thermodynamics, offers a potential bridge between gravity and quantum mechanics. It also reframes the idea of an edge. In a holographic universe, the edge is not a physical boundary, but a computational limit, a mathematical screen on which the illusion of reality is rendered. And beyond even that lies the unsettling possibility of emergent spacetime, the idea that space and time themselves are not fundamental, but arise from deeper, non-spatial, non-temporal processes. In this view, the fabric of the cosmos is not made of matter or geometry, but of entanglement, information, and correlation. Spacetime emerges like temperature in a gas, not as a thing, but as a behavior of underlying constituents. This shift is supported by recent work in quantum gravity, tensor networks, and the study of black hole entropy. If spacetime is emergent, then the edge of the universe may be an illusion born of emergent perception. There is no boundary, only a limit to the scale at which space becomes meaningful. So, where does this leave us? Are we any closer to finding the true boundary of the universe? The short answer is, maybe not in the way we imagined. What the final confrontation reveals is that the edge is not likely to be a physical wall, a spatial cliff beyond which nothing exists. It is more likely a conceptual boundary horizon in our models, a limit to how we define place and existence. And the battle is no longer just between instruments and nature. It is between models, frameworks, and worldviews, each compelling, each incomplete. Yet, amidst this chaos, there is extraordinary progress. The Event Horizon Telescope, for instance, has imaged the shadow of a black holy triumph of technology, theory, and global collaboration. LIGO and Virgo have detected gravitational waves, confirming predictions Einstein made a century ago. The Planck satellite has mapped the cosmic microwave background with unprecedented precision, revealing the fingerprint of inflation. And the James Webb Space Telescope is peering back in time to the earliest galaxies, testing our models of structure formation. Each discovery narrows the field, challenges assumptions, and sharpens our questions. In parallel, physicists are working to unify these approaches, not by choosing one theory, but by identifying the underlying principles that must hold true across them. Causality, unitarity, symmetry, information, conservation. These are the guideposts. The dream is to find a theory of everything, a single framework that encompasses gravity, quantum mechanics, and the large-scale structure of the universe. It may not resemble any current theory. It may emerge from an entirely new mathematical language. But the path to it lies through confrontation, through the honest clash of ideas, the rigorous testing of assumptions, and the humility to admit when our tools fall short. The future of cosmology lies not just in bigger telescopes, but in deeper questions. Missions like LISA, Euclid, and the Roman Space Telescope will map the dark universe. Quantum computing may simulate the early universe at resolutions never before possible. AI will sift through petabytes of cosmic data to find patterns we didn't know to look for. And young physicists, unbound by legacy paradigms, will propose bold new ideas, some of which will be wrong, many of which will be beautiful, and one of which may finally thread the needle between relativity and quantum mechanics. In the end, the final confrontation is not a war. It is a conversation between models, between generations, between the known and the unknowable. The edge of the universe may never reveal itself as a place. But in confronting it, we are forced to refine our tools, our language, and ourselves. And in that refinement lies the real progress. Because the edge is not a thing we find. It is a thing we become aware of, one insight at a time. This is the future of cosmology. Not a final answer, but an eternal unfolding. A story that began with fire, stretched across light, and now spirals into information. A story we are still writing, not on maps, but in questions. And the ultimate question remains, will we ever reach the edge of the universe? Perhaps not. But in seeking it, we reach something greater, the edge of what we can imagine. And from there, the journey begins again. We peer into the night sky not just to measure stars, but to measure ourselves. We build telescopes not only to see farther, but to understand deeper. The exploration of the cosmos in its truest form has never been just about data, numbers, or even discovery. At its core, it is a moral pursuit, a quest that reflects the very best of who we are and who we wish to become. To explore the unknown is to engage with the most ancient of human impulses, curiosity. And through that curiosity, we are not only driven to understand the universe, we are invited to understand ourselves. The deeper we go into the cosmos, the closer we come to the foundations of meaning. In a universe that may have no edge, no center, and perhaps no final answers, what matters most is the act of asking. And in that act, there is a lesson, maybe the most important lesson our species has ever learned, that truth is not a possession, it is a path. Every discovery we make is a reminder that knowledge is not a destination, but a relationship between us and the unknown, between our limited senses and the boundless reality that surrounds us. The stars do not speak, but they reveal. The void is not empty, but full of questions we are only just beginning to hear. Curiosity is the engine of science, but it is more than a tool. It is a moral force, an ethical instinct that says, we could turn away, we could accept what we have, but we will not. We will ask more, we will learn more, we will go further. That impulse, irrational in its persistence, often unrewarded in the short-termists, the same impulse that created the first fire, carved the first tools, crossed oceans, decoded genomes, and now listens to the echo of the Big Bang. Curiosity is not the luxury of idle minds. It is the signature of intelligence, the hallmark of civilizations that endure. And the cosmos rewards it not with comfort, but with awe. Because what we find out there, beyond the safe edges of our certainty, is not always what we expect. The universe is weirder than we imagined, filled with forces we cannot see, energies we cannot define, and questions we may never fully answer. And yet, this tension between what we know and what remains hidden is not a flaw in science. It is its greatest strength. To live in a state of wonder, to dwell in the balance between knowledge and mystery, is to remain open, and that openness is where wisdom begins. The cosmos teaches us to relinquish ego. It shows us that we are not the center of anything, and that's exactly why we matter. In a universe that does not revolve around us, our attention becomes a kind of reverence. Our search becomes a kind of prayer. This is the moral heart of cosmic exploration. The willingness to live inside questions bigger than ourselves, not to conquer them, but to grow alongside them. To be humble before the vast, and yet never paralyzed by it. Every equation we write, every satellite we launch, every theory we refine, is an active participation in something unimaginably large and yet, somehow, intimately connected to our own minds and bodies. We are made of stars, not metaphorically, but literally. The carbon in our cells, the calcium in our bones, the iron in our blood, all forged in the hearts of ancient suns. The atoms that now think and feel and wonder were once part of explosions that lit up the young universe. What does it mean to know this? What responsibility does it carry? It means that when we look outward, we are also looking inward. That when we ask, what lies at the edge of the universe? We are also asking, what lies at the edge of ourselves? This reflection is not abstract. It is ethical. Cosmic exploration challenges us to expand not just our knowledge, but our compassion. To see our planet as fragile, not fixed. To see our differences as small, not insurmountable. From space, the divisions we cling to, nation, race, class, dissolve into perspective. The Earth becomes a single shimmering whole, and all of us, passengers on it. This is not poetic sentiment. It is what astronauts report again and again, that the overview effect changes them. That seeing the Earth from space rewires the heart. That distance brings clarity, not detachment. And yet, the moral takeaway does not stop at unity. It asks more of us. It asks us to be brave in the face of uncertainty. Because the truth is, we may never find all the answers. We may never know what came before the Big Bang. We may never detect another civilization. We may never confirm the multiverse or measure the total shape of space-time. And that's okay. In fact, that's part of the lesson, that the value of science is not in finality, but in the refusal to give up, that the real triumph is in the pursuit itself. To continue to explore, to continue to ask, even when the answers are unclear, even when the data is incomplete, even when the mysteries only multiply, this is not failure. It is integrity. In this light, scientific progress is not just the accumulation of facts. It is the cultivation of virtues, patience, discipline, honesty, imagination, and above all, humility. The cosmos humbles us not by diminishing our worth, but by enlarging our context. It teaches us that we are temporary, but not irrelevant. That we are small, but capable of thought. That we are limited, but able to glimpse the unlimited. In that paradox, there is dignity. And in that dignity, there is a path forward not just for science, but for humanity. The balance between knowledge and mystery, then, is not a compromise. It is a kind of dance. We move forward. The universe shifts. We ask, it responds, sometimes with clarity, sometimes with deeper silence. But always, there is motion. Always, there is room to grow. And as long as we stay curious, we are never truly lost. The edge of the universe may recede forever, but the edge of understanding moves with us. It grows as we grow. And perhaps that is the greatest gift the cosmos offers. Not answers, but the capacity to seek them. So what can humanity learn from all this? That knowledge is sacred, but not enough. That curiosity must be paired with responsibility. That intelligence without wisdom can be dangerous. That the more we know, the more we must care about our world, about each other, about the fragile conditions that allow this rare thing called life to exist at all. Cosmic exploration is not just a journey through space. It is a journey into ethics, into perspective, into character. And in the end, perhaps the universe does have a message for us, not written in stars or carved in radiation, but embedded in the very structure of the journey itself. That the unknown is not to be feared. That mystery is not a void, but an invitation. That the search is not something outside of it is us. And if we are wise enough to keep searching, brave enough to keep asking, and humble enough to accept what we find, then maybe, just maybe, we will learn not only where we are in the universe, but who we are because of it. This is the moral arc of cosmic exploration. Not conquest, not certainty, but wonder, awareness, and transformation. A long, slow turning of the human soul toward the infinite. Not to dominate it, but to belong to it. And in that belonging, to become something greater than we were. Not because we found the edge, but because we never stopped looking for it. In the end, as we reach the final pages of our cosmic journey, not with a definitive map, but with an ever-unfolding trail of stars behind us and darkness ahead, the most important question remains. Should the mystery of the universe be solved, or should it remain open? Is it better to know the final truth, to reach the ultimate edge, to close the book of questions with a clear, confident answer? Or is the true value of this journey found precisely in its incompleteness, in the open-ended nature of the universe's grand puzzle? To answer this, we must return to the heart of what it means to explore, to wonder, and to seek knowledge not as a possession, but as a purpose. There is immense value in answers. Throughout history, our species has thrived by unraveling mystery show to make fire, how to navigate the seas, how to cure diseases, how to land on other worlds. Each solution changed us. Every answer became a foundation on which the next great leap was built. Science has advanced because we insisted on clarity, on evidence, on conclusions drawn from careful testing and observation. So it's natural to want the universe to yield its secrets in the same way. We want to know where it began, how it will end, whether it has boundaries, whether we are alone, whether everything we experience is real or a hologram, a simulation, a layer of information written on some deeper reality. To answer these questions would be to affirm our place in the cosmos. It would anchor us in a sea of possibilities. It would be a moment of clarity in a sky filled with noise. And yet, there is another kind of value. One not found in conclusions, but in openness. In the refusal to finalize the story. Because sometimes, when a mystery is solved, its magic fades. The allure, the wonder, the imaginative power of not knowing that too has its place. When we look up at the stars, what we feel isn't a calculation, it's a connection. A sense that we are part of something unimaginably vast, and that part of us will always remain small in comparison. That tension, the known versus the unknowns, what keeps curiosity alive. It is the spark that drives scientists, artists, poets, philosophers. To close the mystery would be to end the dialogue. To open it forever is to keep the story alive. In cosmology, some questions may truly have no answer, not because we haven't found it, but because the question itself transcends the scope of testability. What lies beyond the observable universe? What came before time? Are there other universes? Are we real in the way we think we are? These questions may remain forever at the horizon of human understanding. And maybe that's not a flaw. Maybe it's the most important feature of reality, that no matter how far we go, there will always be something further. Another layer, another question, another edge that turns out not to be an edge at all, but a door. And perhaps that's the real purpose of science, not to close the book, but to add chapters, to expand what is possible, to make the unknown more beautiful, not less. And in the process of asking, we discover more than facts. We discover values, patience, perseverance, humility, imagination, we realize that knowledge is not just about facts, it is about perspective. The further we go into space, the more we see Earth not as the center, but as a fragile, brilliant outpost of life. We learn that the cosmos is not cold, but complex. That time and space are not rigid, but responsive. That we are not alone, not yet, with other minds, but certainly not isolated from the forces that shaped stars, galaxies, and ourselves. The atoms in our bodies, the thoughts in our minds, the questions we escall, are part of the same story that began billions of years ago. That is not an answer. That is a relationship. So, what are the biggest takeaways from our journey to the edge of the universe? First, that the universe is bigger, older, and stranger than we ever imagined. It expands faster than light, contains more galaxies than grains of sand, and is shaped by forces we still don't understand. Dark matter, dark energy, and the vacuum of space itself all suggest that what we see is only a fragment of what exists. Second, that theories compete not because scientists are divided, but because they are searching together for frameworks that make sense of the evidence. String theory, loop quantum gravity, multiverse models, and the holographic principle all represent different attempts to unify what we observe with what we believe to be true about the nature of reality. Third, that the future of science will depend on questions we haven't asked yet, tools we haven't built, and minds we haven't yet inspired. The limits of observation, the constraints of light speed and cosmic horizons, the challenge of reconciling general relativity with quantum mechanics, these are not dead ends. They are invitations to innovate. Fourth, and most profoundly, that the pursuit itself is meaningful. That even if we never reach a final answer, the act of exploring expands who we are. It gives us identity. It gives us purpose. It gives us a shared story that transcends borders, languages, and generations. And this is why the conclusion of our journey must remain open-ended. Because the mystery of the universe is not a riddle to be solved. It is a landscape to be explored. An idea that keeps unfolding. A horizon that recedes as we approach. To demand a final answer would be to miss the point. The cosmos is not here to be conquered, it is here to call us forward, to challenge us, to reflect us, to humble us, and to remind us that no matter how far we go, there is always something more. This is the power of an open ending. It is the breath held just before the next revelation, the silence that invites the next question, the space that says, we are not finished, we are not done. We are still learning, still dreaming, still becoming, and the universe, in all its infinite possibility, is still speaking. So, let it remain open. Let the edge stay undefined. Let the mystery continue, not because we fear the answer, but because we love the asking. And in doing so, we honor what it means to be human. Not a creature of certainty, but of wonder. Not a being who needs all the answers, but one who can live inside the question. That is the final thought, the lasting truth, the moral compass and the scientific call. There is no end to space, because there is no end to imagination. And for as long as we look up and wonder, the universe will never truly be silent. It will always have more to show, more to teach, more to become, and so will we.